Welcome to all of you. In the previous class, we have discussed about the weak interactions and one of its unit. Now, we will continue that. We will come to the dipole interaction. Now, first we have to understood what is a dipole. Dipole means having two poles. That is, two poles will have opposite properties. Now, how in molecules dipoles are created? Suppose we have a molecule of HBr, hydrogen bomb. Now we know that if a system is of the type A and A, that is, if the molecule consists of two atoms, A and A, that is the same atom, then the electronegativity difference will be zero. And they will share that bonding pair of electron equally in both the sides. And hence, they will not possess any kind of charge. But if this is system AB, then electronegativity difference will occur, En difference will occur. And what will happen if there is electronegativity difference? Suppose electronegativity of A is less than that of electronegativity of B. What will happen? The electron pair in that covalent bond will be pulled more towards B. And then a charged species, partially charged species will generate. And B will acquire some delta minus charge and A will acquire some delta plus charge. Why B acquires some delta minus charge? Because that paired electron is shifted slightly towards B. That is, B don't accommodate the entire pair or A don't lose the entire pair. That is, there is a balance between them. They don't lose either of them. So we have a polar system. Now, these kind of polar system will try to have a special arrangement between themselves. So what will occur? An interaction, attractive interaction will occur between the B minus, B delta minus and A delta plus. And these attractive interaction is known to as the dipole-dipole interaction. We can see such molecules in heterodiatomic molecules. And if the electronegativity difference is large, then the dipole-dipole interaction will increase. And if the electronegativity difference with hydrogen atom and between some other atoms becomes too large, then it will lead to hydrogen bond. We will discuss about hydrogen bond a few time later. But first, let us see some other factors regarding that dipole-dipole interaction. If we consider the dipole-dipole interaction in the stationary state, now, what is stationary state? Stationary state means in fixed state. Means where the orientation of the entire system is fixed, like in the solid state. Then the dipole-dipole interaction force FDD represents the dipole-dipole attraction force, will be proportional to the 1 by third power of R. And if the state is not stationary, that is, if the molecules are rotating, for rotating molecules, for rotating molecules, for rotating molecules, that FDD is proportional to 1 by 6th power of R. That is, if the molecule rotate, then the dipole-dipole interaction will decrease. That is, dipole-dipole interaction is much more weaker for the gaseous or the liquid state, where the molecules have a chance of rotation. But in solid state, this dipole-dipole attraction is much more higher. Now, let us see a similar kind of forces as that of dipole. Suppose if one system is dipole, suppose if one system is dipolar, suppose we have HCl. This system is dipolar and we have carbon dioxide, CO2. This is a non-polar system. This is non-polar and this is polar. Then polarity may be induced in that non-polar system due to presence of that polar system. And these kind of interaction are called dipole induced dipole interaction. Now, in dipole-dipole interaction, what happens? Suppose we have a system AB with B is more electronegative than A. Then what will happen? The system will get polarized. This is B delta minus and this is delta plus. Now, that system will induce some other non-polar system to act as a polar system, or it will induce polarity to the non-polar system. Suppose this AA is a non-polar system. Now polarity will be induced in that system. And what will happen? An attraction force will be in between them. So what will happen? We will again get F dipole. We will again get if dipole-induced dipole interaction, dipole-induced dipole interaction force. Now that force will be proportional to 1 by 6th power of R. That force is proportional to now 1 by 6th power of R. So what we get? We get again that if we have a system, if this is polar, then three kind of forces may act between them. Dipole-dipole forces, dipole-induced dipole, and along with that, London forces will work. So these are the three weak interaction that we learned about. Let us recapitulate again. We have first learned the London force or or sorry, spontaneous dipole force, London force, or spontaneous or instantaneous dipolar interaction or dispersion force. Second, we learned about dipole-dipole interaction. Dipole-Dipole interaction. And finally, we learned about dipole-induced dipole interaction. So, along with that, we will go for another force, the hydrogen bond. Hydrogen bond is not as weak force as that of London force, dipole-dipole force, or dipole-induced dipole interaction. Now let us see in which case we have the probability to observe the hydrogen bond. Hydrogen bond is very necessary, because if the hydrogen bond do not exist, then the tertiary or quaternary structure of the proteins may not exist. And if those structures didn't exist, then we will not have our enzyme work. We may not be living. This hydrogen bond is also responsible for the density of liquid H2O to be greater than that of the solid H2O. We all know that the ice floats on water. Why? This happens only because of the hydrogen bond. Due to formation of the hydrogen bond, the water molecules in the liquid state come very closer to each other. But in solid state, it is not possible, and some vacant space is created. And due to this, ice floats on water. Floating of ice in water. Floating of ice in water. Structures of protein. HF. We know that HF is not an acid. HF is not an acid. And for all these phenomena, one thing is responsible, the hydrogen bond. Now, what is the hydrogen bond, and in which cases we will observe hydrogen bond? We will observe hydrogen bond when hydrogen will be attached to oxygen, fluorine, or nitrogen. We can consider H bond as an extreme case of dipole-dipole interaction. Extreme case, extreme case of dipole-dipole interaction. This is an extreme case of dipole-dipole interaction. Now, why this occurs? Let us see some facts. We all know that electronegativity of hydrogen in Pauling scale is nearly 2.4. That of electronegativity of nitrogen is nearly 2.8. That of oxygen is approximately equals to 4, or slightly less than 4, and that of fluorine is exactly 4. So here fluorine is the most electronegative atom, is the most electronegative atom, and it has also higher electronegativity than oxygen. It is approximately equals to 4 for case of oxygen, but electronegativity of fluorine is equal to 4, and these all data are given in the Pauling scale. Pauling scale of electronegativity provides this data. Pauling's scale of electronegativity. These data are given by that part. Now what happens? Why I'm saying that this is an extreme case of dipole interaction. When hydrogen is bonded to some very much electronegative species, then what happens? This electronegative species gets a delta minus charge and that gets a delta plus charge. But the charge separation, the extent of charge separation is too much. So that part now is free to interact with another hydrogen atom, another adjacent hydrogen atom very frequently, and that chain is carried forward. And we have a system like that where the hydrogen atom interacts with electronegative atom of another molecule. So this is the fact that hydrogen bond occurs. This is a very strong dipole-dipole interaction. So now we will discuss about hydrogen bond later in chemical bonding. We will go for some other example. We will learn also some question answer, but not in this class. For now, we will try to recapitulate the class again. What what are the things that we have learned previously? For that, we have started with the weak forces. In weak force category, we have dispersion force, dispersion force, and dipole-dipole and dipole-induced dipole interaction. Now, these are the weak forces. Along with these forces, we have discussed hydrogen bonding, and some of its importance. In the next class, we will opt for the thermal interactions or the thermal energy. Thermal energy. Then we move to the gaseous state. Thank you for watching. Now this class will be terminated and we will come with the thermal energy and gaseous state for the next class.